Hello everyone, and welcome to my final project presentation for CS50 Cybersecurity. My name is Adam Sheikh, presenting from Al Ain, Abu Dhabi, in the United Arab Emirates. For academic integrity, administrative verification, and course tracking, my edX username is Adam1625, and my GitHub repository username is AdamSheikh309. Today's recording date is the 21st of June 2026. In this technical brief, we are going to perform an exhaustive system and cryptographic analysis of CVE-2026-29000. This is a maximum severity critical authentication bypass vulnerability discovered in March of 2026 within the widely used open source Java security framework component, pac4j-jwt. Because this vulnerability allows remote, unauthenticated attackers to bypass secure login controls and fully impersonate any system user, including domain administrators, it has been assigned the absolute maximum CVSS severity score of 10. I selected this incident as the focus of my CS50 final project because it serves as an excellent, real-world manifestation of a fundamental concept we explored heavily in the course's cryptographic and application security modules: the critical and often catastrophic mistake of confusing data confidentiality with data authenticity. Over the next few minutes, we will look at how a seemingly minor logical oversight in a Java security library can turn a public key into a master login key, allowing an attacker to completely cross a network's trust boundary. To establish our baseline, let us first examine the core technological parameters of JSON Web Tokens. To understand why this vulnerability occurred, we must first review the security foundations of stateless token architectures. In modern web environments, systems rely on JSON Web Tokens, or JWTs, to pass user identities back and forth without forcing the server to keep track of stateful database sessions. Now, under standard cryptographic design rules, there is a strict divide between confidentiality and authenticity. Confidentiality is managed through encryption. In a JSON Web Encryption, or JWE, setup, a payload is encrypted using a public key so that only a receiver holding the matching private key can read it. It answers the question, who is allowed to view this data? Authenticity, however, is managed through signing. In a JSON Web Signature, or JWS setup, a cryptographic signature is generated using a private key or a shared secret. It answers the question, who actually wrote this data? And can we guarantee it has not been modified? The fatal flaw at the center of CVE-2026-29000 is that the library treated successful decryption as proof of authenticity. It assumed that because it could decrypt the incoming payload using its own private key, the claims inside the token were safe to trust, completely ignoring the fact that any external client can encrypt messages using a public key. Let us trace the structural architecture of the vulnerable pac4j-jwt framework to see how this looks inside the system. Under normal, secure software operations, a security framework should follow a strict fail-fast layout. This means that when untrusted user input enters the application, the signature must be validated before any of the data is processed or constructed in active memory. However, in the affected versions of the pac4j library, the internal processing flow takes a dangerous, linear route. When a user sends an encrypted token, the JWT authenticator begins by decrypting the outer JWE container. Once decrypted, the system immediately proceeds to parse the payload and extract key identity markers like names, email addresses, roles, and administrative flags. The application architecture sets up a scenario where parsing and state preparation run ahead of security validation. This design decision means that unverified, untrusted user claims are actively handled and processed in memory before the library has checked the signature to verify if the token originated from a trusted issuer. Let's zoom in on the source code level to pinpoint exactly where this logic collapses. As you can see on the slide, we have a simplified representation of the library's internal logic. When handling an encrypted token, the system executes a method called toSignedJWT on the decrypted payload. It assigns this to a variable named signedJWT. If the token contains a normal signed payload, the signed JWT variable is populated, and the execution enters the conditional checks. Inside those blocks, the signature is validated against the application's configuration. But look closely at what happens if the inner token is unsigned. Under the JSON Web Token standard, it is completely valid to have an unsigned token, known as a plain JWT, where the signature block is simply omitted. If an attacker packs an unsigned token inside the encrypted shell, toSigned JWT returns null. Because signed JWT is null, the program bypasses the signature check condition entirely. It silently skips the verification step, yet the program continues down its linear path and executes create JWT profile. The core vulnerability is this silent conditional fall-through. By failing to check if the signature was present and required, the library allowed an unsigned token to bypass the entire security check. Decryption succeeded, and the library mistakenly accepted this as a valid pass. Because of this implementation loophole, the exploit sequence is incredibly straightforward and requires no complex cryptographic attacks or brute forcing. First, an attacker obtains the target server's public RSA key. Because public keys are intended for public distribution, they are easily harvested from TLS certificates, public configuration files, or public JWKS endpoints. Second, the attacker crafts an entirely forged, unsigned JSON Web Token. Using standard formatting, they set the subject field to an identity they want to hijack, for example, a system administrator, and write elevated privilege parameters directly into the roles array. Because this is a plain JWT, they omit the signature entirely. Third, the attacker takes this forged token and encrypts it using the server's public RSA key, generating a structurally valid encrypted JWE container. Finally, the attacker sends this payload to the target application's authorization interface. The application successfully decrypts the payload using its private key, encounters the unsigned inner token, silently skips signature validation, and builds an active administrator session profile in system memory. The attacker now has full root access over the host, resulting in a total authentication bypass. To prevent this vulnerability from exposing systems to takeover, security teams must deploy structured, multi-layered mitigations that reflect the core defensive engineering lessons of this course. First, the direct fix is to upgrade the application's dependencies. The maintainers of the pac4j framework patched this vulnerability by releasing versions 4.5.9, 5.7.9, and 6.3.3. The patch alters the verification logic. If the system expects a signed token and encounters an unsigned nested structure, it immediately triggers a secure failure state, throws a cryptographic exception, and discards the token before it can affect application memory. Second, developers must enforce strict signature algorithms. This means explicitly configuring system parameters to reject the none algorithm type and verifying that the inner token matches the expected cryptographic configuration. Most importantly, we must internalize the system design lesson of CVE-2026-29000. Confidentiality is not a replacement for authenticity. Just because a server can decrypt a message does not mean the message is authentic. By applying zero-trust data validation, keeping software dependencies updated, and verifying authentication claims at the boundary, we can build secure systems that can withstand sophisticated network attacks. Thank you very much for your time and for reviewing my final project presentation for CS50 cybersecurity. Again, my name is Adam Sheikh, and this concludes my presentation.